So as Tom said, I'm Mark Corliss. I'm an application engineer out of the Novi, Michigan office. Did anybody come to the FPGA prototyping session? A couple over here, look at this. So in that session, you saw a motor that was spinning. It was using a rapid prototyping situation with an FPGA. In this session, we're going to talk more about a production code generation type of workflow. What do I mean by that? I mean, you've been hearing a lot of it throughout the day, but I would like to kind of encapsulate some of that information into kind of what I call 4 boxes. So from a very high level, model-based design for motor control, we have this motor that we want to be able to control, and in a very modeling sort of way, similar to what Steve Miller said in the Simscape session, sometimes the things that you need to control are too difficult to control, or too big to control, or you only get one chance to control it. So this leads people to start creating models of the things that they want to control. You saw Ed from Cummins this morning talk about how important it is to select the right level of fidelity for the design task at hand. In this case, our design task at hand is to develop a controller algorithm which will be implemented as embedded software. So we can create a mathematical model of our motor. We can then create a mathematical model of our controller components. We can gain some insight through simulation. Simulation is great. It allows us to do more work away from the lab. It allows us to save time. But eventually, most of us have products that we're developing, and we want to actually create something, and for that something, it's an embedded system, and we need some type of code. And this is where embedded coder comes in, helps us take this algorithm and get nice, efficient C code out of it. As Ed from Delphi just talked about, this is actually the point where sometimes you will have conversations between the controls engineer and the software engineer in order to balance off this, making sure that what you simulate is obvious and readable, as well as getting the type of code that you need for your implementation. The controller code by itself is good. It's mathematically the same as what you simulated, but the controller code by itself isn't enough to just spin the motor. To spin the motor, we need to integrate that with a hand-coded software project. You've seen several examples of that today. Blake from Daimler called this the base project. You might hear me refer to this as a parent project. But typically in a model-based design workflow, for production, we generate code for the algorithm, we integrate it into this handwritten project, and we treat it very similar to how we would treat hand code. So from a high level, this is pretty straightforward, 4 boxes. What I like to do over the next few minutes is make it a little bit more real, kind of take you through a design iteration, set the stage for some of the things that we might continue to talk about with the panel session when everybody comes up. So for this, we'll leave PowerPoint. We like Simulink, but for a moment, we're going to go to an embedded development environment. This is Code Composer Studio, just one of, every embedded system has an embedded development environment. We just happen to choose this one. Freescale's got some really nice stuff too. In this environment over here, this is our handwritten project, but included in our handwritten project is code that was automatically generated from embedded coder. And if we take a look at this code that was generated from embedded coder, this code was generated Tuesday, May 12th, 1558, so it's fresh. Once we've generated that code, we call it from our interrupt service routine, just like you would call some other piece of hand code. And you can work with it in your embedded environment just like you'd work with other pieces of hand code. So for example, this is a watch window in Code Composer Studio. Let me pull up. That's funny. See, I expected to see a video there. Okay, hold on. Let me disconnect the. Hey, now I see a nice little video there. All right, so this is a motor. It's connected to a embedded processor running C code. And then I can do the types of things that I would expect. Probably in simulation, I turn the motor on, I turn the motor off. I would control the speed, keep going faster. Then one of the interesting things happens when you leave the simulation environment and you go to hardware. Sometimes you start doing things that you didn't test in simulation. Now, you could build a good case, and a lot of the verification stuff that you should be doing more in simulation. Love simulation. It's not uncommon, though, that in hardware, you run into a situation that you didn't run into in simulation. So this happened to us. So what happened was, one of my colleagues was in the field, and he said, velocity command, oh, this is nice. Can I go to, like, negative 400? And at first I think I'm going, because I'm decreasing. It's aliasing, so it looks like it's spinning up and slowing down in the video, but it's basically slowing down and going to stop. This is a graceful stop. When this was happening to us in the field before, the whole board would reset itself. And this was frustrating to debug on hardware because the board just keeps resetting itself. So my colleague called me up and he said, hey, I'm running into this issue. I'm like, okay, well, let me take a look at that. I don't have the hardware in front of me. I don't want to wait till he comes back to the office and work in the lab. He needs me to start debugging stuff now. Well, because this algorithm came from a model, what I can do is I can go back into the simulation environment and see if I can reproduce the issue. So we'll close this guy off. So here's the Simulink model of the system. It's kind of what I would call a classic architecture. We have some system inputs. We have the controller algorithm itself that we'll take a look at in a little bit. We have a mathematical model of the stuff of the hardware that's sitting in front of me. Just to give you an idea what's inside of this mathematical model, it's basically, there's a model of the three-phase motor. There's a PMSM. This is from the product SimPower Systems. It's basically a DQ model. And it's parameterized by a bunch of variables, which means that we can kind of have data and we can configure the model to map the different hardware that we have in front of us, or we can run different Monte Carlo tests and do different robustness analysis on it. Steve Miller was talking about how one of the advantages, so this is this block here is actually a combination of kind of Simulink and Simscape. One of the advantages of Simscape that he was talking about is the ability to just kind of like bolt things on. So we have a disk load, and the disk is basically just an inertial load, and we can just hang it off the network. So this is a simple example of some of the types of things that you can do with the physical modeling tools. But the only reason that we do all these things with the physical modeling tools is to gain some insight, right? So let's go ahead and run this simulation. Go ahead and run it. We'll let it go again. So this is the test that I had done for myself before I sent my colleague out in the field to do a demonstration. I didn't know that my colleague in the field was going to do something else. So this worked here. It stepped from 0 to 100, comes back down. He was basically stepping from like 0 to or 400 and back down again. So Signal Builder, I think you've seen that in the previous session today. It's one way that we can author signals. There's multiple ways. So from here, I'm going to say, what happens if we make this velocity command 400? And then we'll step down to minus 400, right? What do you guys think is going to happen? I wish I had a t-shirt, but I don't. Am I going to get any good insight? Goes up. Oh, I guess I should resize the scope so we can see. Yeah, and then comes down. And go back. I said to my colleague, what are you talking about? It just works, right? So my simulation, it works, right? And these are the types of things that sometimes happen, right? Something worked in simulation, but when you went into the field, something was a little bit different. What's different? There's some dynamic going on out there that we didn't capture in the model. Those of you that have been doing motor control are probably figuring out what that is. What's interesting, though, is even though the simulation didn't fail, I can still get some insight from it, right? Because now I'm asking myself, okay, well, what's going on here? I know that in simulation it looks good, but on the hardware, something weird is happening. I'm going to start poking around. Well, when I start looking around, and I take a look at the DC current, which is this green line, when we switch directions, all of a sudden I'm pushing like a couple of amps of current back into the board. Now, Some boards can handle that. This one in particular can't. In fact, I know I can only push about a half an amp of current back into the power supply before it shuts down. See, if you remember, I said the original time I ran into this, the whole board just shut itself down, the power supply would go green. So I said, well, I should be able to design an algorithm that prevents this from happening, because I can't fix it in hardware at this point. The hardware already exists. And I can do this in simulation. Now, how I fix this is going to be dependent upon kind of who I am and how I want to approach the problem. Some of my colleagues are battery guys, right? And what they might do is they might say, okay, well, what I actually want to do is make a better model of the battery or a better model of the power supply. And I can say long term, that's a great thing to do. But the point of this model is for me to be able to test software. So I can just add a test into this that says, hey, if I push a half an amp of current back in, just shut things down. So in this verify outputs, what we did is we basically added an assertion block. So if you're in the HMI session, you saw Jason do something similar when he's debugging for HMI. And I'm going to enable this assertion. What this is going to do is it's going to detect if I push a negative half an amp back into the system. So I'll run the system. All right, so I go up. Life is good, life is good. Hold 400, no trouble. I try to change speeds. When I try to change speeds, then pretty quickly, then it can throw an error back to the user. So even though I haven't, even though some of my physical modeling guys would say, hey, I could make a better physical model, me as a software engineer, this is great. I have a little test going on over here. I can make sure if I do something, this doesn't break. Now, in this design, actually, for the sake of time, I've actually already have the feature built into this system. So in other cases, I might show you how I might build it up. For the sake of time, the feature's in there. I just need to turn it on, right? And I can turn it on based on a variable that Simulink is talking to. Now, historically, Simulink would always be talking to variables in the MATLAB workspace. Was anybody ever frustrated when Simulink would talk to variables in the MATLAB workspace? They weren't. That's good. For those that might have been, one of the things that I heard a lot of was we wish we had another container which was its own file that I could revision control that wasn't the MATLAB workspace. And that's where this data is in. It's in the data dictionary. And I can access the data dictionary using this lower icon in the lower left. I can click this button to open it. And the parameter that's inside of it is, I called it dynamic current limit enable, and it's off. So I'm going to go ahead and turn it on. One of the nice things about the data dictionary is that because it's its own file somewhere else, it knows if you've changed something. So I've kind of made a local change, but I haven't really committed it. I haven't changed the file that's in revision control. I'm just playing around with it. That's why it tells me it's modified. It's different than the value that's checked into revision control. Now, I could just hit play, right? And I could say, hey, is this feature doing what I thought it was going to do? But you might be asking yourself, well, this parameter over here, how is it associated with the model? Where's actually, what's reacting to this parameter? So in order to find that, I can right-click on the enable, and I can say find where used. We'll look inside. Sure, go ahead and update diagram. Oh, there we go. So it's actually used in this model. If I were to kind of have this over here more, to double click, it'll kind of flash that it's here. So basically, this is the feature that I can find the feature from the data dictionary. And basically, all the dynamic current limiter is doing is based on the velocity that I measured, I'm going to limit how much current is going to go back into the motor. Now, one of the things that you might have noticed is that, this model isn't the same as the top level model that I used. In fact, if I went back to the test bench model and looked inside of it, yeah, there's another model over here, right? So you might be asking yourself, well, how many models are being used in the system, and how is the system architected? How can I get some insight into that? Well, typically, what I recommend is that each this is my recommendation. This is not 100%. There's a lot of successful ways to do this. For the types of things that I've worked on, I typically have this mental model of kind of one reference model per function call that I want to generate, or one reference model per something that I want to attach to an interrupt service routine. So you'll see is that this test bench model is basically wrapped around this algorithm model, and it's this algorithm model that we'll generate code from. But you also kind of notice there's some other models going around. So this one model has other models. And I can go to Analysis, Model Dependencies, and I can take a look. And I can get kind of a bird's eye view of my architecture. That I've got this test bench model, I have the model that I'm going to generate code from, I have a current controller model, and a velocity controller model. Now, one thing that happens when you start having multiple models in your design, each model has its own configuration set, and the configuration settings for these things need to be synchronized. Another advantage of having this data dictionary is that I can point all of these models to use the same configuration set. So if I make a change to one parameter in the configuration settings, it gets propagated to all of the different models that are sharing it. Before I generate code from this guy, Ed from Delphi, he made this made this notion of kind of the balance between kind of the software engineer and the controls engineer. And I want to talk about a couple of different modeling things that we've seen that help communication between the software engineer and the controls engineer. One of the first is that we normally have this layer, we have blocks, that basically convert between the raw integer units that come from a driver, like the counts from an encoder, or the integer value that comes back from an analog to digital converter, and the physical units that are in the system, in volts or amps, and the same way in the other direction back out to peripherals. This is an interesting debate sometimes, because sometimes people will say, well, I can get the most efficient code if I never worry about these units. Typically what happens, though, is when you're in the field and you want to debug something, having the right units in front of you really helps from a debugging point of view. It really helps from a communication point of view. So we typically recommend that. Then if I go inside of this thing that's wrapped for the units, what we'll see off to the left is we have a state flow chart. The state flow chart's basically, its job is to schedule the different components and the tasks. Some of the components are basically simple enough to be subsystems. Other of the components, once we schedule them, we'll have a reference model inside of them in order to partition out the design. So this is a high-level view of the architecture and stuff. At the end for the Q&A, if you have other kind of architectural questions, we're happy to kind of continue talking back and forth. But from this model, this is the model that the top-level model I generate code for this interrupt service routine. Now, I could just hit this build button over here and start generating C code from it. What we found is when you get started, this is a great way to do it. Often what happens, though, is your project starts evolving and multiple people are working on it. It's often nice to have more of a MATLAB script or an automated approach to do this. So here I'm using a Simulink project as a container. So I have all these different files and stuff. They all have relationships with each other. One way that you can kind of contain a group of files together is called Simulink projects. One of the things that Simulink projects allows you to do is create shortcuts. What I mean by shortcuts is if I look at all of the different files that are related to this design, to a new user, all of a sudden you're like, what are all these files? I don't know what's going on. Often what you want to do is provide insight to just a subset of things. This is where shortcuts come in. So for shortcuts, for this example, we basically just have two primary things that we do. We either open the test bench in order to run simulation, or we can generate C code and copy to the parent project or the base project. I'm going to go ahead and run this guy. Now, you'll also notice that in addition to generating code, you'll see that we're creating some other artifacts and stuff. Like Bill from C&H was saying how the interface is really important and making sure that different things work together. By scripting this out, this allows you to maybe do some additional checks on the code that you're going to generate or on the model itself, or maybe package things up or make additional artifact files that might be useful later on in the design process. Then when it's done, it'll create a code generation report. And especially when you're getting started, the most interesting of it tends to be this code interface. This basically tells the name of the function and all of the different arguments that are passed into it, along with their data types. If they're fixed point, it'll tell you where the radix points are. Each of these different arguments are associated with ports in the model. So basically, input ports in the model and output ports in the model map back to the arguments in the function prototype control. In addition to arguments that you might pass in or out, you might have some of these other controller variables. So remember, we enabled that that current limiting, the dynamic current limiting algorithm. And there was a variable that I used in the data dictionary, but that variable also shows up into the generated code. So for example, for whatever reason, my brain's not seeing it. Dynamic current limit enable. So what's interesting is my brain, for whatever reason, I can't see it through here. But if I go back to the design, let's go back to the component where I know it was. I say, okay, well, this is the block that had it. I can right-click on it and say C++ code, navigate to code. Okay, and then it'll find it. Then it'll find where it's used for me as well. If it's used in multiple places, it'll find different places wherever it was declared or wherever it was used. And then there's also traceability back to the model itself. So if you run into situations that I ran into there where all of a sudden you know you're looking for something but you can't quite find it, what you can do is you can hyperlink back and forth between the two and have traceability. So at this point, I have generated new code. I automated copying it into the Code Composer parent project. Let me stop Code Composer. And if we go back to Velocity Encoder, will she be smart enough to update? Yeah. 431, so she knows it's new. Let's go back and debug. So by clicking the debug, it's basically going to find the files that were generated. It's going to recompile the project. So now we'll go ahead and connect to her again. Here's the design. So we'll ask for, we'll start with 100. There was 100. There was 400. Then the moment of truth, minus 400. Yep. And she goes through and she spins back the other way. Now, ironically, what I meant to do in there, but I forgot, was to actually run the simulation where I showed you that it worked as well in simulation. But I'm guessing that because it's working on hardware, you're probably going to believe me that it was working in simulation as well. I apologize that I forgot that important step. But from a very high level, so basically what I've done here is from a very high level kind of walked you through kind of the key steps in a simulation to production code generation task. Just did some highlights over what some of the modeling techniques look like, some of the debugging techniques look like, some of the code generation and integration techniques look like.